Picking up right where we left off, section 8B-1, perimeter and area of polygons. The next part we're going to talk about was using trigonometry to find the area of a triangle. Now, this is it's a pretty straightforward method, and a good way to tie it into previous material is with side angle side. Let's make a little split right here. Tie it into side angle side, which we've seen previously for triangle congruence and triangle similarity. Okay, now we're only dealing with one triangle in these cases, so it's not the same. Again, it's the pattern that we're going to use here. Because if we have a triangle, any triangle, obtuse, acute, it doesn't matter. As long as you have a triangle, X, Y, Z, if I have this pattern, I can use trigonometry to find the area. Because an alternative to the common formula, 1/2 base times height, is 1/2 B times C times the sine of A. This is a generic way of writing the formula. Maybe we should use a different letter. Let's use, since it's area, we don't want these two areas to be confused. So let's use a different letter here. Let's use the letter D. Again, just so that those two A's don't get confused. Alright, so BC times sine of D. So again, the important thing here is that we have a side angle side relationship. Alright, so side angle side. So again right here, let's say we are given XY here. Let's say that's 15. And let's say that XZ over here is 27. So if I'm going to have a side angle side relationship, which of the three angles do I need here? Well, side angle side, remember, the A angle has to be included. It has to be included, meaning between the two sides. So the easiest way to determine where that included angle is, well, look at the two sides. Which vertex connects these two sides? So it would be X, because 15, let's use red to emphasize it a little bit more. 15 is this side right here. And on the 27, let's use blue, is this side over here. So which vertex connects the two? X does. So this is the included angle. See? Side, angle, side. Alright, so let's say, just throwing this out there, I know I have a protractor, but I don't want to measure this thing, so let's just call this, let's say this is 35 degrees. So now, since we have two sides and the included angle, well, we can use our formula to find the area. Again, that's all we need. If we don't have that height, if this is the only information we're provided, then we can still find the area using this particular method. So the area is then 1/2 15 times 27, and A and the B and C are interchangeable, so we could have put 27 times 15. That doesn't really matter. Thing is, you don't want to mix the one thing is you want to make sure that the 35, since that's the angle, goes into the sine. You do not want to mistake 35 for B or C. Sine of 35. Typically, I like to leave the 1/2 at the end. Deal with all this first. So let's show all the steps. So 15 times 27. So we get 1/2 405 and times the sine 35. So we can just jump into that with the calculators. So times 35 sine. Yep. So 1/2 232.2984567. Then 1/2 is the same thing as dividing by 2, so divide by 2. 116.1492284. So if we round, in this case, let's round to the nearest tenth. Oh, whoops. The area is approximately 116.1 square units. I didn't say feet or inches or anything, so we're just going to call them square units. If anything, I'll do an additional example. This is just something I kind of put together to explain the formula here. Alright, so again, this formula is found on page 3 of the PDF. And then below that you have the area of a regular polygon. So now let's talk about that. Okay, so first a review of what is a regular polygon. Well, regular polygon, congruent sides, congruent angles. That's what makes a polygon regular. All the sides are congruent, all the angles are congruent. So that makes finding the perimeter really easy. Because if you have the length of one side, well then you have the length of all of them. Okay? So it's just a matter of determining what kind of, how many sides does the polygon have and multiplying it by the length of the side. Really, really quite simple. Okay, now area, that's a different story. Okay, so let's do right here, regular polygon area. Okay, so for the area of a regular polygon, again, this only applies to regular polygons. We're going to address later how to deal with strange looking polygons, but for regular polygons, there is a formula. A equals 1/2 lowercase a times p. The capital P here stands for perimeter. So you can't find the area of a regular polygon without first finding the perimeter, which again is simply, we'll call it S, that is an S, not a 5, times N, where S is the length of one side and N represents the number of sides. So now what about this lowercase a? Well, that lowercase a is something called the apothem. I've heard it pronounced apothegm. I don't know the correct pronunciation. I work with numbers, not language, so I say apothem. You're not going to be graded on that, so apothem. So what is this distance here? How does that work out? What's it for? Well, let's add context. Context clears everything up. So let's make a, let's see. Let's work with a hexagon. Hexagons are a nice even number. That's okay. It's not going to be too big. Okay. 4, 5. Okay, there we go. Doesn't look right, but it should be. So again, right here, we made a 3, 4, 5 triangle. So 3, 4, so there should be 5. And these sides over here will be 5 as well. It looks weird, but let's roll with it and say that this is a regular hexagon. It's a regular hexagon. So what is the apothem? Okay, well, the apothem is the perpendicular distance from the center of the regular polygon to any one of its sides. The center of the polygon. Okay, so let's see. We have 2, 4, 5, so that should be about right here. So that should be about right there. Just occurred to me why this is not a regular hexagon. But again, let's pretend that it is. Okay. So here's the center. So if I take this distance, or this point, and I find the perpendicular distance to any one of these sides, then that's going to be the apothem. Again, it has to be a perpendicular. It's a perpendicular distance to a side and not a vertex. So from here down to there. That is our apothem. Okay, if you're given the apothem, well, then that makes everything really easy, because then it's just, you take the length of the side again, and that's, any one of these 6, since they're all congruent. But then we need to find the apothem. If you have so you can use this side to find the perimeter, multiply it by the apothem, divide by 2, boom, you have your area. Now you're not always going to be given the apothem. Where's the fun in that? So how do you address it if you're only given the side length but not the apothem? Well, let's talk about that. Again, we'll do we'll do one example here, and then in an upcoming video I'll do some additional examples to address all the formulas. That way we cover all our bases there. Okay. So what do? Let's say the side length is 11. Okay, so let's take this figure again. Let's assume it's a regular polygon, and let's say that the side length is 11 centimeters. And we want to know, well, what's the area of this figure? And we know, well, we don't have the apothem, so what am I going to do? Well, I'm going to start with the perimeter, since that's really easy. It's a hexagon, so there are 6 sides. So n is equal to 6. S is equal to 11 centimeters. So perimeter, S times n, 6 times 11, 66 centimeters. Oh, there. Oof. Took care of that first part. Now the apothem. Well, one of the great things about your regular polygons is that they can be divided into 6 congruent triangles. So see, if I take that center and connect it to the vertices, let's do it the easy way. Making my life hard. Close enough. We end up with our 6 congruent triangles. Now, why does that work? Well, in a regular polygon, that center is not only the center of the polygon, but of a circle that can be circumscribed around the polygon. So circumscribed means that it goes around the figure such that each vertex is on the circle. That's a quick example over here. And this is as close to a perfect circle as I can get without a compass. So let's say I have this circle here, and I pick this point, this point. Let's just pick a handful of points. And then we connect them. One, two, three, four, five. This would be a circumscribed pentagon. It's a polygon with 5 sides, so it is circumscribed because all 5 vertices are on the circle. So that's what circumscribed means. So now if I find the center of the circle, let's assume it's right here, and then I connect that center to each one of these vertices, well, remember the distance from the center of the circle to a point on the circle, well, and that's a radius. So all these distances must be congruent. So we know that each one of these blue lines is a radius of the circle that goes around our regular polygon. So they're all congruent. So not only do we have 6 congruent angles, or sorry, 6 congruent triangles, they are all isosceles. They're all isosceles because the 2 lines here are going to be congruent to each other. So let's label that. There's a lot that goes into it, so this is a pretty lengthy piece of the lesson. So now, before this gets all cluttered up, let's isolate the triangle so we can focus in on it. Okay. I'm going to double it in size. A little use of similarity there. So 2, 4, 5. Okay, well, should be about right there. Yeah, should be about right there. Yeah, we know that this triangle is isosceles. So a couple of things. Since these are the 2 congruent sides, these are called the legs of the isosceles triangle. And then this side over here, the side of the polygon, so let's go ahead and label that 11 since we know that our side is 11 over here. Okay. This would be the base, right? Again, isosceles triangle. The legs are the congruent sides. The third side is the base. Across from the base is what we call the vertex angle. Now, when we make the perpendicular line, the altitude, from the vertex angle to the base, remember when we discussed this previously, that bisects the angle up top, and it bisects the base. So that means this distance here, 5.5, 5.5. What about the angle? How do we figure that out? Well, let's revisit our polygon up here. Remember, we have 6 congruent triangles. So these angles are all going to be congruent. So how many degrees do we have in a circle? 360. We have 360 split 6 different ways. So 360 divided by 6 what is going on here? There we go. 60 degrees. Okay, all that madness. So that means let's label it using blue. to reference the whole thing. So the whole thing is equal to 60 degrees. Since that angle gets cut in half, that means we have 30 degrees right here and 30 degrees over there. So now we can solve for our apothem using trigonometry. Now we can use trigonometry again. So sine, cosine, tangent. Now the good thing here is that it's always gonna be tangent, right? Because this side right here, well, that's your hypotenuse, right? Here's the 90-degree angle, so that's gonna be the hypotenuse. So these two legs here, these two sides, those are your opposite and adjacent. So when it comes to this part of the area of the polygon, it's always going to be tangent. So we say tangent of 30 degrees is equal to opposite divided by adjacent, 5.5 divided by a. If you recall, when the variable is in the denominator of your trigonometric function, you can make our lives easy with a little swap. Instead of doing the whole multiplying both sides and dividing, we can do it 2 and 1 by swapping these two sides. So a is equal to 5.5 divided by tangent of 30. I go to our calculator. 5.5 divided by 30 tangent, which gives us 9.526279442, which, let's go ahead and round to the nearest tenth. 9.5 centimeters. So now that we have our apothem, we can go to our formula, find the area. So our apothem is 9.5, our perimeter was 66, so 9.5 times 66, so then divided by 2, so 313.5. So the area of this triangle, this regular hexagon will be 313.5 square centimeters. Okay, so just to include the work here, it's kind of weird to put it in the middle here, but that's kind of how the paper worked out, so let's kind of swoosh in here. So again, since the area is 1/2 the apothem times the perimeter, our formula becomes 1/2 9.5 times 66. 9.5 times 66. Gotta save some space right here. 627 divided by 2. 313.5 would be our final answer. Okay. So we'll stop right there, and then we'll go on to talk about circles.